Okay, we're going to get started with homework 5, part A. The question is, using the heat and mass transfer analogy, derive and explain the Lewis relation, i.e. H equals QCP air times KC. Okay, so first what we got to do is, in order to relate these expressions, we need our mass and heat transfer terms. So we're going to start with our Sugarwood, Schmidt, Nizza, and Prandtl numbers. So let's okay, we're recording. Let's write those down. So hold on, let me get situated. There we go. So we're gonna start. Let's start with our Sherwood number. So for Sherwood, we know that that is going to be our KCL over our D from A to B. And then we can do our Schmidt, which we know is our viscosity mu over our rho DAB. We have our Nozell, which is HL over K. And we have our Prandtl, which is CP viscosity over, that's really bad. Oops. Over K. Okay, and then we're going to rewrite our Sherwood and Nuzelt numbers in terms of our other ones. So what we're going to do is we're going to write our Sherwood as our C times our Reynolds number to the 1/2 power times our Schmidt number to the 1/3 power. And then we can also write our Nuzelt number as our C to the Reynolds number times E to the 1/2 multiplied by our Prandtl number to the 1/3. Sorry, our C times our Reynolds number, I don't know why I said R, times E to the 1/2. And then when we combine these terms, like all of them, I guess, we can get a value that is going to be our SH, so our Schmidt number over our Nuzelt number, which is going to be equal to KC times L times K over P times A to the B times H times L. Then we can cancel our L's here. Oops. Yeah. Then when we cancel our L's, I must have got rid of my other L. We're going to get just SC over PR to the 1/3. As we can see, it will be KC times KC over PAB times H. So that's how we derive that term. And then if we rewrite it one more time, we can get, if we rewrite it one more time, so let me just write rewritten. We can get K over rho CP from D times from A to B to the 1/3 power. And that's going to be equal to LE 1/3, which is equal to KC K over DABH. Now we can solve for H when this value here is to the 1/3 power when that is equal to 1. So when that's equal to 1, we're going to end up with a value that is just going to be H is equal to KCP times, oh sorry, it's going to be K C times rho times Cp. So now that we have our part 1 done, we can move on to the second part, which is derive and show the relationship between wet bulb temperature and the adiabatic saturation temperature. From this, derive an expression for the molar concentration of water in terms of dry and wet bulb temperatures. So we're going to start with evaporative cooling, and then we will move on. So our evaporated cooling, we need to relate our heat and mass. Let's write this. We need to start writing stuff down before instead of talking. So we're going to have to relate our heat and mass when heat is equal to H times A times delta T. And when our mass is equal to K times A times delta C. And then when we relate those terms, we are going to get HA, and then we can write out delta T, which is going to be T air minus T water. And that's equal to KC A CW minus C infinity. And then when we need to multiply by our gamma as well. So now we can sub this term into what we did in part 1. So when we sub that in, we're going to get KCP times CPA, and we're going to get T air minus T water is equal to gamma KCA times CW minus C infinity. And then we can cancel terms out, so we can take CP or C, KC, KC. Our rho and our CP is going to have to stay. We can cancel areas out, and I think that's all that we can cancel. So when we rewrite it, we're going to get rho CP times T air minus T water, which is equal to gamma change in C. Okay, so what we're going to do next now is we're going to have to do an adiabatic saturation temperature, where our temperature of water will eventually reach our temperature of air. So when we know this, we can get, since we know our H or water and our H air are equal, we can do HA T water 2 minus T air 1 is going to be equal to that value that we solved for. Which that value is going to be KCA, yeah, just our concentration air minus concentration air 1, I think. That seems right. And I'm reading a multiplier gamma through. Okay, so that looks pretty good so far. So, now we need to, I believe this is a part where we have to add in a known value, which I don't have, so I'll be back once I have that. Okay, so I just wrote the term missing up above, here in red, and then now what we can do is, we're gonna keep moving and simplifying. So we're gonna get KC rho times C rho or CPA, and we're gonna get T air 1 minus T water 2 is equal to our KCA times C air 2 minus C air 1 gamma. Well, now we can cancel Kc, A, very similar to what we did above. So we'll end with rho Cp T air1 minus Tw2 is equal to, here, let's put the gamma out front, gamma C air 2 minus C air 1. Now we need to solve for C air 2 minus C infinity. So when we do that, we'll get C air 1 minus C infinity, and we just know just C air 2 is just what we're referencing. This is going to be equal to rho Cp T air 1 minus Tw2 all over gamma. Okay, cool. So now we just have to solve for C infinity, and our dry bulb temperature for that, our T infinity will be our dry bulb temperature, and then our T air 2 will be our wet bulb temperature. So once we do that, we'll get this should be T air 2, not T air 1. So when we solve for C infinity, we'll get C air 2 minus rho Cp T air 1 minus Tw2 all over gamma. And like I said, this our T infinity is a dry bulb. And then when we solve for our C air 2, we get the same thing, but just with our C infinity. Okay. There we go. That was a relatively shorter video showing how we can use heat and mass transfer analogies to derive Lewis relationships, and then use those in specific instances like adiabatic saturation temperatures, and how we can find terms of dry and wet bulb temperatures.